finishing up chapter 2 today, properties of light. So far we've gone over some of the basic foundational principles of light and optics, basically what is light. We've talked about the electromagnetic spectrum, we've talked about light as rays, waves, particles, we talked about Einstein's equations, we talked about the energy equations, E equals hc over lambda, E equals h nu. We talked about atomic transitions and how atoms can absorb energy and give off energy, and if you're lucky, it's in the form of light. But today we're going to shift gears a little bit, and we're going to talk about the measurement of light. And again, usually I put this part of the course after laser safety, but because to study laser safety you have to understand how to measure light properly, I figured I'd shift the order. I put chapter 2 ahead of chapter 1, the order of chapters. So the measurement of light basically involves the measurement of electromagnetic radiation. And there's two ways of looking at how to measure light. If you are looking at the measurement of electromagnetic energy where wavelength doesn't matter, okay, you're looking anywhere from X-rays all the way up to microwaves, radio waves, and everything in between, that is the field known as radiometry. Okay, radiometry is a science in and of itself, and people spend their whole lives and careers as radiometrists studying electromagnetic energy. If, however, you focus your attention to just the visible portion of the spectrum, okay, where all light measurement is based on what the human perception, what your eye sees, that is the field of photometry. And there are distinctions and similarities between the two, and that's what we're going to be talking about today. All right? So, the first thing, and this is probably the most boring part of this course, and I promise the rest of this course will not be this boring, but when we go through different units, it's a real sleeper, so just bear with me. When we talk about radiometry, or radiometric measure, radiometric units, these are the units that we use when we're talking about electromagnetic energy, regardless of the wavelength. Different terms that you'll see, radiant energy. People sometimes confuse or use words interchangeably, like energy, power, intensity, irradiance, brightness. There are actually meanings to those particular terms. So when we're measuring the radiant energy, how much energy is being given off by a light source, we're talking about energy that is measured in joules. Okay, so this is the unit of joules, and we'll talk more about that. Okay. Radiant power, sometimes called radiant flux, okay, is designated as P. Sometimes it's F. F is when it stands for fluence. But in this course, generally we deal with power in terms of watts. And power is basically energy per unit time. How much energy is being delivered over how much time? When you take those two and you divide them, you get power. The units for power are joules per second. Another word for joules per second is watts. Okay? Watts, milliwatts. Okay? That's a radiometric measurement. When I use my power meter here to measure the laser power meter, okay, this measures watts. Okay, or it actually measures milliwatts, but this is a radiometric tool. Okay. When we look at, there's a term called excidence. You don't really see excidence too much, but if you go into the lighting industry, radiant excidence is the power emitted per unit area of a source. So if you have a light source, let's say it's a globe bulb, looks like it's this big, and you have a certain area over this surface, how much energy or power is being emitted per unit area? So the unit for that is watts per meter squared. Sometimes milliwatts per meter squared, sometimes milliwatts per centimeter squared, but basically power over area. That's how much light is coming out of the source. If you take the light that's coming out of the source and measure it over here, how much light is striking the surface, depending on the surface area and the amount of power striking that surface area, you get another term called irradiance. If all of the light from this source falls on another source, the irradiance on that source is equal to the radiant excidence, okay? So if all of this falls on the surface, then these two are the same. The units are the same, watts per meter squared or watts per centimeter squared, but irradiance is the more used term. We use irradiance a lot in this class, especially when we get into laser safety next week. But irradiance is, if I take a laser beam, and we'll do some calculations in a little bit, but if I take a laser beam, and I shine it on my hand, okay, what is the irradiance on my hand? Or if I shine it on the wall, what is the irradiance up there? If you know what the area is, okay, this beam is probably 1 to 2 millimeters in diameter, okay, so you have a diameter there. If you know how much power is in here, you calculate the area, take the power divided into the area, watts or milliwatts, or per square centimeter, or per square meter, and that will give you the irradiance of this laser beam. And that's very important because when we're looking at laser safety, one of the things we're going to be looking at is how much laser light does it take to damage your eye. These things are considered eye safe. Well, this one really isn't eye safe. If you shine this in your eye, you will cause retinal damage because this is about 20 milliwatts. Again, when we get into laser safety, you'll see that the maximum, we're going to study something called the maximum permissible exposure. Maximum permissible exposure is how much irradiance is allowed to fall on your eye and hence hit your retina, because your eye does focus from the back of your eye onto your retina. But how much irradiance over how much period of time can you withstand before you cause retinal damage? So in order to calculate that, determine that, you need to be able to calculate the irradiance of whatever light source you're looking at. So this is an important one. This one here, and these two often get confused, irradiance and intensity. Okay? Intensity actually, in the optics field, actually has a very specific meaning. Intensity is measured in something called watts per steradian. Anybody ever heard the term steradian?
Only in the book.
Only in the book, okay. But it's source power radiated per solid angle. Okay, you think, all right, what is a solid angle? Well, if you consider this to be a point source, let's say an infinitely small source of light, and this is giving off light in all directions, okay? If I take, and I'm going to try to do this here, I'm going to make a cone, okay? And assuming this starts from an infinitely small point and extends outward, okay? The cone of light that comes out of that, okay, will create something called a solid angle. It's like a three-dimensional angle. It's not just this direction, that direction, but it's also in this direction here. That is what we call a steradian. It's a unit of solid angle, and we'll talk a little bit about it in a second. But radiant intensity, when you're actually measuring the intensity of the light coming out of the source, you have to consider it to be a solid cone emanating from that source, and the area on the top of that cone is one of the measures that they use, how much light's in that cone. So, a lot of terms, the important ones for you to remember are energy, power, and irradiance. Okay? We don't really deal with excidence because we're not really studying light sources. This is more limited to white light sources. We deal primarily with lasers in this class, so the sources are very concentrated. Usually, all of the light that's coming out of the laser is striking the surface anyways. I mean, that's the idea. So we deal with irradiance. Won't really get into intensity, but we will talk about it a little bit here. I won't expect you to remember intensity. Okay, let's look at radiant excidence. Okay, the radiant excidence is the amount of power that radiates or exits a source per unit area. Its units are power divided by area, watts per square per meter squared, and it's basically used to characterize light sources. For example, let's say you have a globe lamp. You see a globe lamp, so things that you hang in your apartment in the corner and on a rope. Let's say the globe lamp is rated at 40 watts and has an 8-centimeter diameter. Okay, so you've got this globe. It's actually kind of a small globe, maybe about the size of this thing. And we want to find its radiant excidence. And let's ignore, because light bulbs have a base to them, okay? So if we just assume the bulb itself is just round, okay? Okay, so we're making an assumption there that's giving off light in all directions. So how would you find the exitance of that? Well, we know that exitance is power per surface area, okay, not area. What's the area of a sphere? Okay, I don't expect you to remember, geometry or, from high school, the area of a sphere. But the area of a sphere is 4 pi r squared, where r is the radius of that sphere. So if we have an 8 centimeter sphere, okay, 8 centimeters is 0.08 meters. Okay, and if we want to express this in watts per meter squared, we want to make sure that we have the right units here. So the easiest thing is just to convert this to meters first. So 8 centimeters is 0.08 meters. Half of that would be the radius, because this is the diameter. So we plug our radius in there, so 4 pi times 0.04 meters squared, which gives us a surface area of 0.02 square meters for that light bulb. Then if we take our power, 40 watts, and divide into it 0.02 meters squared, we come up with 2,000 watts per meter squared. Sounds like a lot, but you're basically looking at distributing that 40 watts of power, okay, over an entire area. So if you extend it out to a meter squared, okay, the answer would be 2,000 watts per meter squared. Okay, irradiance. This is more important. Okay, this is something that you need to understand. Okay, so pay attention. All right. So irradiance is the amount of power per unit area that strikes a surface. Like exitance, its units are power divided by area. This can be expressed in either watts per meter squared, milliwatts per meter squared, milliwatts or microwatts per centimeter squared. Depending on what the application is, different units would apply. But for this course, most of the measurements that we make are in watts per centimeter squared. When we talk about lasers for industrial materials processing, they always talk about the irradiance of the focused laser beam on a piece of metal. It's always watts per centimeter squared. So in this example, a laser pointer emits 5 milliwatts of power and has a diameter of 2 millimeters. Sounds reasonable, sounds like the thing we just looked at. Find the irradiance in watts per square centimeter. Okay? Again, irradiance is power divided by area. Okay? Power is given to you. It's 5 milliwatts. We can just leave that. Okay? The area we have to calculate. Now the area, assuming that this is round, okay, what's the area of a circle? Okay, pi r squared. You guys should remember that, right? Okay. One of the things I like to do, and this sometimes messes people up, is because we usually deal with diameters in here. You take a beam, you measure how big it is from side to side, and that's the diameter of the beam. I like to use the diameter version of the area equation. So we know that the radius of a circle is 1/2 the diameter, right? So if I plug in diameter divided by 2, and then square that, I get pi d squared over 4. So diameter squared divided by 2 squared, which is 4, gives us this equation here. And I like to use this one. It's just one step less to do. So if you're given the information in diameter, you could use this one. All you have to do is cut the diameter in half and then use the pi r squared one. But I like pi d squared over 4. So in this particular case, first thing we want to do is convert millimeters to centimeters. And you can do this in your head. 2 millimeters is 0.2 centimeters. If you know that, that's fine. Just plug it in. But this is just, I put this in here because it's just an exercise in unit conversion, which is very important in physics. So if we take our 2 millimeters, remember the rule? Okay, set up an equality that you want your answer in centimeters. So what's the relationship between centimeters and millimeters? 1 centimeter is equal to 10 millimeters. So these two things are the same. When you divide something by itself, you get 1. So you're really not changing anything. Just multiply it times 1. But what this allows you to do is cancel out the millimeters. Okay, do the math. 2 divided by 10 times 1 gives you 0.2. So it's just, this is I like to use it as a sanity check whenever I'm doing conversions, whether it's feet to miles, inches to meters. I always draw out the units. So this would be the diameter, and this is the diameter that gets plugged into d here. Okay, so we get pi times d squared, okay, 0.2 centimeters squared divided by 4. Now when you square this, you square in the 0.4, but you're also squaring the centimeters. Okay, so you get whatever this number comes out to be, 0.04 centimeters squared times pi divided by 4. If you do the calculation, it comes out to 0.0314 centimeters squared. Okay? So this is the area that this is being concentrated in. Okay? If I take and calculate my irradiance now, power divided by area, 5 milliwatts, laser power, divided by its area in centimeters squared, gives us the units of milliwatts per centimeter squared. And if you do the math, it comes out to 159.16 milliwatts per centimeter squared. Okay? 159 milliwatts per centimeter squared. Is that a lot or a little?
It's a small area, but there's not much power, I don't know.
So, well, the human eye, as we will learn next week, okay, has a maximum permissible exposure. The maximum permissible exposure, again, we'll go over this next week, but the maximum permissible exposure is based on a quarter-second blink response. So if you get a laser beam, you know, if you hit an eye with that, your natural response is to be able to blink and turn away in a quarter second. So that's where they come up with the number. Okay? And the number for the human eye is 2.5 milliwatts per square centimeter. If you exceed 2.5 milliwatts per square centimeter, you can potentially cause eye damage, okay, retinal damage. This is 159, okay? It's a lot more than 2.5. So just keep that in mind. Even if you buy these little laser pointers that, you know, you tease your dog or your cat with, those are only about 4 or 5, you know, less than 5 milliwatts, usually about 3 or so. Those are still bright enough to cause retinal damage if you take it and hold it up to your eye for more than a quarter or half a second or so. You can cause some damage. Same thing with your pets, so be careful. So this is how we calculate irradiance, and it's used not only in determining laser safety specifications. We will also use the irradiance calculation to figure out safety goggles. Okay? When you're working with higher powered light sources, laser sources, you know, you need to protect your eyes. How do you figure out how much filtering capability you need in your set of laser safety goggles? This is how you do it. We'll talk more about it. This, by the way, is about 10 times brighter than the sun. When you're in second grade, what do they tell you? Don't look at the sun. During the eclipse, you know, you built those little boxes with the pinholes so you can view the eclipse. The whole reason for that is they don't want you staring at the sun and getting your irradiance focused down into your eyeball, to your retina from your eyeball, and burning a hole. Okay, so we talked about intensity. Okay, this is kind of the best way I can depict intensity and steradians. Okay, steradians is kind of a difficult quantity to wrap your brain around. But if you look at a sphere, okay, and you look at the surface area, okay, that one of the words I use in optics is subtends. Okay, so it's subtends an angle of omega. So consider this to be a cone, and that cone, when it hits the surface, has a certain amount of area to it. Okay, it has a certain radius depending on how big the sphere is. The farther out you go, okay, the larger that area is going to be, and the larger the radius is going to be. So this this unit omega here, this is the unit for steradians. And steradians is equal to the area, this area, divided by the radius squared, okay, as you're coming away from the center of that object. So let's take a look at that. Example, what solid angle is subtended by a 10 square centimeter circle on the surface of a balloon 50 centimeters in diameter, and then by the entire balloon surface? You could also ask the question, if you consider Earth, you know, and you know what the area is, the surface area of Alaska is, you know, what is the angle, what is the steradian angle created by the state of Alaska, you know, if you want to look at it from a solid angle standpoint. So to calculate the solid angle here, it's just area, that surface area, divided by the radius. So we get 10 centimeters squared, okay, divided by 25 centimeter radius squared, okay, gives us 0.016 steradians. Now that is just for a surface area of 10 centimeters squared. If we consider the entire balloon, what is the entire balloon area? Well, if we take the balloon and assume it's a sphere, remember the equation for area of a sphere is 4 pi r squared. If we take 4 pi r squared and divide it by r squared, the r squared goes away, and we come up with a number of 4 pi steradians. So one of the standard units is, if you consider the solid angle, it's kind of like looking at the equation for the surface area of a sphere. The solid angle equation for a sphere is just equal to 4 pi, regardless of the size. 4 pi is 4 times 3.14159. Okay. Finally, radiant intensity. If we look at radiant intensity is the amount of power emitted by a point source into a solid angle. So if we want to find out what the intensity is of that sphere giving off light, okay, we need to know what the power is, we need to know what the solid angle is. So for a sphere, okay, if that solid angle, we just figure it out, is equal to 4 pi, then the intensity given off by a sphere is just whatever's power is coming out divided by 4 pi for a complete sphere. And that, the units would be in watts per steradian. There's another type of light source. Not all light sources are round. Sometimes you have like fluorescent bulbs, how much light is being given off by that. You have to calculate it a little differently. That's called an extended source. And we actually call that unit radiance, how much power, again, by the surface area of a cylinder, I guess, if you're talking about a fluorescent bulb. Anybody ever heard of the inverse square law? The inverse square law says that whatever light source you have, okay, if it's emanating from a sphere, okay, spherical light source, okay, the intensity of the light will drop off as a function of the radius squared. So the farther you go away from the light source, okay, the intensity of the light coming from it is going to go down by a factor of the radius squared, so at a square rate. So in this example here, we're going to derive the inverse square law of radiation for a point source of light. Point source of light, again, is one of those fictitious physics ideal cases where you have an infinitely small source of light that's giving off light equally in all directions. So solving this, the inverse square law, if we take our equation, intensity is equal to power divided by 4 pi for a sphere. The surface area of a sphere is given by 4 pi r squared. So if we know what the surface area is, okay, we can substitute that into the irradiance equation. And for some reason here we're using E for irradiance, but irradiance is power divided by area. If we plug our area in here, okay, which is 4 pi r squared, and we plug for power, if we solve this equation for power, power is multiply both sides by 4 pi. Okay, power is equal to the intensity times 4 pi. So we have 4 pi times the intensity divided by 4 pi r squared, which is the area. The 4 pi cancels out, okay, and it leaves us with intensity over radius squared. And what this shows you is that the irradiance, okay, how much light is reaching the surface, okay, is equal to the intensity divided by the radius squared. So the farther away you move from the source, its radiance is going to drop off by a factor of the radius squared. All right, that was fun, right? As they go. All right, so that's radiometry. Photometry. Photometry is a little more interesting. At least you can relate to photometry. You can see it because this is what your eye sees. So photometry is basically the measurement of the properties of visible radiation as observed by the human eye, and it applies only to the visible portion of the spectrum. These graphs and charts, they're not exact because no two people have the same eyes. Okay, all the eyes are different. But this is an empirical graph based on lots of research, different people looking at different colors and somebody figuring out which colors are most sensitive. But what they came up with, and it's called the CIE chart, which CIE stands, it's a French chart, it's an acronym, but it refers to the International Commission on Illumination. So if you can figure out how to say that in French, that's where CIE comes from. But they have something called the luminous efficiency curve. And the luminous efficiency curve basically maps out the spectral sensitivity of the human eye. If you notice, we have wavelength on the horizontal axis and luminous efficiency on the vertical axis. And what this shows is that the human eye is most sensitive to the green part of the spectrum. Okay? in the green part of the spectrum, and this is basically normalized. When we say normalized, we take the maximum value, we divide every other value by that to so that the maximum value is 1, and everything else is a fraction of that. So the human eye is actually most sensitive to light of 555 nanometers, which is the yellow-green part of the spectrum, peak sensitivity. And what this shows is that if you are looking at red light, for example, let's say 640 nanometers, which is, let's say, over here, laser pointing. Okay, 640 nanometers, okay, if you come up and then you go over, it's only 2/10 of the sensitivity as the eye would have in the green portion of the spectrum. Okay, 0.2, which means, if this is 0.2, this red light would have to have 5 times as much power, radiant power, in order to be perceived as the same brightness as the green. So whatever color you see, whatever power you get, it's scaled by where it falls on this chart with respect to its actual perceived brightness. This is a bigger version of that curve, and I throw this in there for your consumption so that when we do some problems, it's easier to go up and go across when we have a graph. But this is the chart we use for calculating luminous efficiency. Now, there's always a conversion when you look at optical power. Okay, power is usually measured using radiometric devices like this power meter. This gives me measurements in milliwatts. Okay, this may measure the actual power being given off by this green laser pointer, this red laser pointer, but it doesn't tell me how bright it is, because your eye is what determines how bright something looks. Remember, I had the violet laser, it was 50 milliwatts, that, it looked like, not even close to just the 5 milliwatt red one, but it actually had 10 times as much power. That's because your eye doesn't see the violet, okay, as well as it sees, the green or even the red. So if you look at it, at 555 nanometers, what that corresponds to is 683 lumens. So there's a conversion factor there. When you look at 1 watt, this is the conversion from radiometric to photometric. 1 watt for radiometric power at 555 nanometers, peak sensitivity of the eye, is equivalent to 683 lumens. Okay, so you've heard the term lumen before, right? You go to the store, you buy a light bulb, and then usually, I don't know if this package has it, but usually light bulbs give off, or they're measured in the number of lumens. If I tell you, this is a 90 watt bulb, okay? How bright is that?
It seems pretty bright.
This seems pretty bright. When you see 90 watts here, okay, that doesn't tell you how much optical power is coming out of it. Okay, what that tells you is how much electrical power is consumed when you use this. But everybody kind of you've been using light bulbs your whole life, so you know how bright a 90 watt bulb is. You know how bright a 60 watt bulb is. You can make that connection in your brain, how bright it is. But it's really not a measure of the brightness. This is the electrical consumption. If you wanted a measure of the brightness, okay, what you would have to do is measure with a power meter of sorts, how much optical radiation is actually coming out of it, what's the optical power, and then convert it to lumens using that chart, okay, to figure out actually how bright it is. And we'll get to the measurement of this in a second. Actually, while we're talking, I want you to think about this. If I said to measure the brightness of this bulb, better yet, if I asked you to tell me how much light is coming out of this bulb. This is a funky green one. I hate these things, fluorescent ones. There's no, you're not going to get rid of them all. LED is the way to go. But if I said, measure how would you measure how much light comes out of this? Any ideas? You took the lab already,
Yeah.
so. But for those of you who didn't have lab on Tuesday, how would you do it? If you look at this bulb, it's not round. Okay, I mean, you might have, take a power meter and hold it up to it, right? but you wouldn't be collecting all of the light coming out of here. How would you do that?
You have to put it into a black sphere.
Yeah. Well, I might as well
Yeah.
show you that. This device here, which looks like the Death Star, this is a device called an integrating sphere. Think of the word, integrating sphere. It's painted like a pearl white on the inside. Okay? The bulb goes right in the center of this, so you screw this thing in. Close this so that you capture just the light inside here. The thing about a sphere is that when the light comes out, okay, it reflects off all of the surfaces. And because it's bouncing all over the place, it gets integrated, it gets blended, homogenized, right? On the side here, there's a slot here, a hole for a fiber optic probe that picks up the amount of light. And if you have a calibrated bulb that you get from the National Institute of Standards, put it in there. You know, this is how much light a 100-watt bulb puts out. Okay? Measure that, take it out, and put your bulb in there, okay, and measure it. You can get an exact measurement of how much light is actually being given off in that by the light bulb. Aside from this, and these come in all sizes and shapes. I have one in the lab for doing little LEDs. It's only about this big. Looks like about the size of a softball. But the whole idea is to be able to collect all the light coming off the source at all different angles and kind of integrate it all together and make a measurement. And we'll talk a little bit more about this in a minute. But that's an integrating sphere. When you buy the bulbs, okay, this says 75-watt light output. Okay, 75-watt output. This is a 75-watt bulb, but it's really not. This is that green bulb I showed you. It basically says it has the equivalent light output of a 75-watt incandescent bulb, because everybody knows 75 watts. Oh yeah, I know how bright that is. Okay, but this only it only uses 20 watts. So it's really it's sometimes confusing because it says 75 watts, but it's not really 75 watts. It actually it only uses 20 watts of electrical power. The important parameter to see is listed down here. It says the luminous output. Okay, this puts out 1,200 lumens. Oh, okay. The lumens is a measure of brightness, and it's converted so that that's what your eye sees. So if I have something that's 600 lumens versus 1,200 lumens, the 1,200 lumens is going to look brighter. Okay, period, because that's what your eye perceives. And I'll show you how to do that calculation. Okay, there's an equation here. There's always an equation. Okay. There's an equation for everything. By the way, why do we use equations in physics?
Because somebody already figured them out for us.
Right, but you have to know how to use those equations. But equations are basically ways of mathematically modeling physical phenomena. Okay, so this just makes it easier to understand relationships between things. So, luminous unit. When we talk about luminous units, this is how you calculate lumens. This is lumens. Okay, luminous units is the product of the value from the luminous efficiency curve, which, depending on what wavelength your light source is, that's going to affect how your eye perceives it, okay, times this number, 683 lumens per watt. Okay, I didn't put the units here, I probably should have. Multiplied times the radiometric unit. So if you have watts over here, okay, then 680 lumens per watts, those watts would cancel out. So if I take my laser power meter and I measure 2 watts of optical power, plug it in here, multiply it times 683, and then go to my chart and figure out, well, it's 600 nanometers. Okay, what's the luminous efficiency at 600 nanometers? That goes here, and that gives you the equivalent luminous units. Okay, let me come back to this one here. We'll come back to this as well. Okay, so for example, calculate the luminous power for a 5 milliwatt helium neon laser. Assume the wavelength is 633 nanometers. Okay, red lasers we use in the lab. They're about 5 milliwatts. How many lumens does that produce? So if we take our radiometric power, okay, which is 5 milliwatts, this is do not forget to do this. Okay, if it's measured in milliwatts, the units for lumens is radiant power measured in watts. So how many watts is 5 milliwatts?
0.005.
Yep, 0.005 watts. Okay, so if you don't know that off the top of your head, just use the conversion factor. Okay, 1 watt equals 1,000 milliwatts. You can multiply 5 milliwatts times 1 divided by 1,000. And basically, so you get 5 divided by 1,000 or 0.005. Okay? So that's 0.005 watts. So don't forget to convert the watts first, okay? Because that's how the luminous calculation is done. So you look at your chart and you say, all right, 633 nanometers. These are nanometers here. You go over, so this is 580, okay, 590, 6, 10, 20, 30, so it's like right around here. And you go up and over, and it's about 0.25, okay? So this is your luminous efficiency. So your radiant power, 5 times 10 to the minus third watts, or 0.005 watts, if you want to use that number, okay? Times 683 lumens per watt, times this coefficient here, 0.25, gives us 0.85 lumens, okay? Think about that. And you're like, wow, there's not a lot of lumens in there, and it's 0.85 lumens. Okay. Why are these things so bright then? I mean, there's more than 0.5 lumens in there, right? That is, I'll give you the answer, that is just at that specific wavelength, okay? If you spread that out over the entire spectrum, okay, if you had a light source equivalent of this, you'd have to have like a 1,000-watt flood lamp, you know, in order to give you that much spectral lumens just over that one small individual wavelength. Okay, so think about it that way. But anyways, this is how you can tell how bright these are. If I had this, you know, if you take the red laser and the green laser, remember I held them up and one was brighter than the other. Okay, the way to really make that measurement is to calculate the number of lumens for each source and then compare it. Which one has more lumens? Okay. We could actually do that right now. Let's say we had, just a quick example here. So let's say we have laser pointer, green. Let's say the green laser has a power of, let's say 5 milliwatts. Okay, and let's say we have a red laser. It doesn't have to be a laser, LED, could be a light, whatever light source, that has a power of 25 milliwatts. Okay, and I asked you, which one is brighter? You might say, well, the red's got 25 milliwatts, so that's got to be brighter. But you don't know, because you have to go through this calculation to figure it out. So if we did that for the green, I said green and I wrote red. Green. Okay. 5 milliwatts. Well, we know what that is in terms of watts, right? Okay. So we get 0.005 watts. Okay. Times 683 lumens per watt. The units cancel out. That's a good thing. Okay. Times. Now we have to go to the chart. Okay. We also have to know what the wavelength of this is. So the wavelength, let's say this is 540 nanometers. That's the wavelength of the green laser pointer. Okay, this one here is wavelength is 640 nanometers. Okay, so for the green, we have to go over to the chart at 540. Okay, so this is 580, 70, 60, 50, 40. We go up. It's like 0.95. Right? See that? Okay. This is from the CIE chart, 0.95. Can somebody calculate this for me? Just crunch out the numbers. Don't all jump at once. Get those awesome TI-30 calculators out.
3.24.
3.24. Can somebody verify that? Okay, you got the same? All right, good. Not that I don't trust you, I just want to make sure they do it. So. Okay, so that's the green. How about the red? Well, you can do the red in red. So for the red, we've got 25 milliwatts, which is 0.025 watts, times 683 lumens per watt, times, now we have to go over to the chart. We're at 640 nanometers, so we have, let's see exactly. So that's 630, 640s right here. Looks like it crosses just about at 0.2. So throw it in there, 0.2. How many lumens is the red? Crank that out. 3.42? Okay. Which one's brighter?
Right.
The red, okay? But it's 5 times the electrical power, I mean the optical power, for it to be perceived by your eye is roughly the same, okay? So that's where this comes into play. It's pretty straightforward. Oh, look at that, I just did that example. All right, so there's another example right there of what we just did. Okay, forgot to do that in there. So let's go back for a second to, okay, so the luminous units, okay? Prepare to get bored again. So, it's not as boring. So, like energy in radiometric terms, in luminous terms, luminous energy is known as the Talbot. You don't see luminous, you don't see the unit of Talbot very often. You might see kilowatt or Kendall power, candelas, things like that. But it's basically radiant energy or joules. Okay? Luminous power, okay? This is where the lumens come from. This is Talbots per second. So this is energy. Energy per unit time, regardless, is what power stands for. But the luminous unit is the radiant power in watts, per watt. Luminous exitance is just like radiometric exitance, is how much light is given off by an object, okay, but corrected for the human eye. Illuminance is the equivalent of irradiance in radiometric terms, so it's how much light, how much irradiance, watts per square centimeter or per meter. And then luminous intensity, again, same as radiant intensity, it's basically watts per steradian, per solid angle. Again, I don't expect you to remember any of these. What I do expect you to do is be able to do those calculations there. Yes?
On the far right, it's not a formula, that just happens to have a slash in it, right?
Yeah, that's just the units. Okay. So, enough of the terms. I hate terms. You can always look up a chart and get the terms. So, some examples. One of the things that is, when you're looking at your light bulb and you want to find out, which one is better, and you want to do the cost-benefit analysis, one of the units we look for is luminous efficiency. Luminous efficiency is how many lumens does that bulb put out per the electrical cost or the electrical power consumed. So for example, if I have a 100-watt bulb and 100 watts of optical power, lumens, and it costs a certain number of watts of electrical power to consume. For example, if we say a 60-watt incandescent bulb, 60-watt incandescent bulb puts out about 800 lumens. Okay, if you think about that, this is the electrical. It takes 60 watts of electrical power to create 800 lumens. If you divide 800 by 60, you get about 13 lumens per watt. Okay, so you can do your math that way. If you look at one of those energy efficient bulbs that I hate, those fluorescent bulbs, they're a little better. Okay, puts out about 800 lumens for about 14 watts. Okay, I guess it's better than 60 watts, right? Okay, until you have to throw them away. You can't just throw them away. But this gives us about 57 lumens per watt. All right. If you look at an LED bulb, I like LED bulbs. LED bulbs are good. 800 lumens only costs you about 6 watts. Okay, so you get about 133 lumens per watt. Okay. Now, even though these are more expensive than these, I'd buy them just because.
Especially at Costco.
At Costco, get them at Costco. Okay. You know what you can also do? What was it, the mass Department of Energy has a special program that will come into your house and do an energy audit.
Mass saves, yeah.
Mass saves, yeah. They recently came into our, we had them come in and they check, you know, your doors and your weather stripping and stuff, but they also will replace all of your light bulbs with LEDs for free. So I have a pretty big house, lots of light bulbs. So I was like, yes.
Yeah, the Eco Builders place right here, they sell them for 3 bulbs for $10.
Yeah.
3 LED bulbs for
Yeah.
$10.
The other,
Yeah, and they last
10,000
years.
hours.
Yeah, it's
10,000
great.
hours is the rating on
Yeah.
it.
How about daylight?
And that's,
What's that?
Daylight.
Daylight bulbs? What do you mean daylight bulbs?
Like the same, or they call it daylight, like the what?
Oh,
it's
those
a
are-
different
Those are
spectrum.
LEDs too.
Yeah,
they're
they're LED
LEDs.
also.
Home
Depends what you mean
Depot.
by,
Yeah,
by
they have
daylight.
All my
They have
house.
daylight and they have,
So, no, daylight.
This is a different light,
Yeah.
this is a different light output, it's
Yeah,
a different.
different spectral content, which is what I was gonna talk about. Good segue, okay.
yeah.
So the cool thing about LEDs, which it's difficult to get in a fluorescent bulb, is that if you look at, and this is, you know, for those of you who did the lab on Tuesday, those, you know, the rest of the people who do it today, but we look at the spectral content of these light bulbs. And the LED bulbs, they have LEDs which are, they are called multi-chip emitters. They have 3 different LEDs in them, a red, a blue, and a green. You combine red, blue, and green, you get white, okay? But you can get these that are tunable. You can change the hue, the color temperature of the bulb. Nick's got an app on his phone where you can change, you know, do you want a warmer light, cooler light? The daylight bulbs, I believe, are those bulbs that try to mimic the spectral output of the sun, which varies through the day. In the morning, you get up, the sun has a much more red, orange and red spectral content. By midday, it shifts to blue and green. Okay, and that actually is, you know, is why people who don't get a lot of natural sunlight have end up getting like seasonal affective disorder, SADS. It's because of it messes with your circadian rhythms. Your body is relying on that color spectrum to produce melatonin. Melatonin is the hormone that makes you go to sleep at night. So, and I know this because we did a project with, there's a company in East Hartford called RSL Fiber Systems. They make submarine lighting, artificial lighting for submarines and for mines, places where people don't get natural sunlight. And the cool thing about it is they use LED light engines. I actually have one, they gave me one. But they deliver the light through fiber optic cable. So, you know, if you're, you know, in a certain part of the submarine, there's just one big light engine that sends the light to different parts of the submarine and, you know, provides the illumination for underwater. Has lots of different benefits. The first one is that you don't have bulbs that burn out. The second one is you get vibrations that, you know, they're more reliable because it's underwater, so it's hermetically sealed. But what they do is they sync up the color temperature of the light to the circadian rhythms. Basically, they try to mimic natural sunlight. So in the morning when the sailors are waking up, they start out with a more red spectral output, and then as the day progresses on, it gets more green, and at the end of the day, it goes back to orange, red, and then orange. Okay, just so that the body thinks it's outside, so that's, you know, the hormones are generated properly, and people don't suffer from seasonal affective disorder. But it's pretty cool. I mean, and these are all because of LEDs. LEDs allow you to do that. The other thing about LEDs is, and I'm a salesperson for LEDs, I just like them. You know what I really like about LEDs? Is these cool flashlights. The flashlight technology has gone crazy. I mean, if you look at this thing, it actually has a square emitter inside. And this thing puts out a crazy amount of light. I just bought some at Costco. They have a pack, it's like $39, and you get one that's smaller one's like 250 lumens, one that's 500, and one's 1,000 lumens. 1,000 lumens is like a spotlight. And it has the focusing head on it, so you can, a lens, so you can focus it. It's, I mean, you know, Navy SEALs use it. You can blind somebody with things. It's like, you know, they're pretty cool. And they're dimmable. You can dim them. Unlike the fluorescents, I hate fluorescents. Okay, anyways, so this is a little chart that I thought you might find interesting, just to show how much these bulbs cost. I forget where I pulled this from. But the lifespan of incandescent versus compact fluorescent versus LED, 1,500 hours, 10,000 hours, 50,000 hours, okay? If you look at the cost of the bulb, and this is misleading, it's not a few years, this is a few years ago, it's like a tenth of this now, these are $3, you can buy one of these things. So it's the same price of these things, which means these things are going away,
Yes.
thank God. You know, but it's still, you know, a little more expensive than the incandescent.
Not to mention the LEDs have advanced even more since then.
Oh, God,
Oh.
yeah, LED technology. You know what's made the LEDs advance? These things. This is the whole reason why LEDs have come as far as they have just in the past 10 years. Fiber lasers. LEDs are essentially the same thing as a laser diode. A laser diode is basically an LED on steroids. But the LED technology, the semiconductor technology that goes into building high-powered laser diodes for pumping fiber lasers for industrial application, the same technology is used for creating super bright LEDs. But if you look at the cost of electricity and running this thing for 50,000 hours, okay, this is the bottom line here. If you ran your light bulbs for 50,000 hours, it costs $900 if you're using incandescent, even though they're a lot cheaper. 210 for the CFL, and only $90. And actually, you could divide this by 3. It's only about $30 because the price has gone down. Well, actually, less than it's like $9 because it's gone down by a factor of 10. So it's a no-brainer. You know, $9 versus $950 for the incandescent. So go out today and get your LED. All right. So chapter 2 is done. I tried to print out the quiz. I'm going to give it to you as a take-home because, again, I won't be here next week. I won't see you until Thursday again. But I have the quiz as a take-home. I tried to print it out, but our printer is broken, of course. And so I posted it on Blackboard under Chapter 2 assignments. It's a PDF, just print it out. One thing I will ask is, if you look at the quiz, there's 5 or 6 questions on it. And I intentionally made them close together, because I want you to do the work on a separate sheet of paper, okay? Take your time, use several sheets of paper, you know? But try to do it as neat as possible. A lot of times I get these things, they're like, you know, there's equations everywhere, on the sides, on the edges, upside down, and and it's like, my goal is to look through just to make sure you understand how to apply what we've learned in solving these problems. So just try to be neat, this is what I'm saying. And do it on a separate piece of paper, you know, so that it's just easier for me to find it. If I can't read the thing, I can't grade it. And I know inevitably, we got like 16, 17 people in here. There's gonna be 1 or 2 people who are gonna try and write the answers between the lines, you know, on the first page. It's like, don't do that. I won't like that. So use separate paper and just try to be as neat as possible. And by the way, show all your work. You know, if you write 8 as an answer, I don't know what that means, you know. It's like, find the power, 8. So make sure you show the equations, the calculations, because even if you get the wrong answer, I'm looking to see if you're using the right equations to solve these things. And I look at your math, I look at the process that you take, you know, so even if you get the wrong number, you still get credit for doing the problem. But if you just put a number there, I have no idea what you did. You know, so just show your work. And also always show your units, okay? Over here, when you're calculating this, okay, watts cancels with watts. The only unit left is lumens, so you know your answer is right. If you don't show your units, then you don't know if you're going down the right path. So try to do that. So I think that's where I'm going to end today. And for those of you who have lab, we'll pick up at 12:30 and try to get some stuff printed out. But take a break. We'll grab some to eat. Have a good weekend. Who's winning the Super Bowl? Panthers.
Whoa.